In my last video, I explained how the servos worked and demonstrated how to control them with Arduino. But I also mentioned that there is a much easier way to handle this by using a dedicated library, which is exactly what we'll cover today. I will also show you how to control positional servo with external input, like potentiometer. Sounds interesting? Then stick around. The Arduino Servo library is a standard library that simplifies controlling servo motors by providing functions for setting angles and pulse widths. It comes pre-installed with Arduino IDE, so no additional setup is required to start using it. Let's do an overview of all the important functions from the Servo library, which help control servo motors in Arduino projects. First, we have attach method, which connects the servo to a specified pin on the Arduino board. You can use simplified syntax or include minimum and maximum pulse widths with slightly more complex syntax to set the servo's range. This actually addresses calibration issues that we encountered in the first part of this tutorial. The write function sets the position of the servo by specifying an angle in degrees. Alternatively, you can use write microseconds, which sets the servo position by specifying the pulse width in microseconds. These two functions handle issuing the impulses every 20 milliseconds, which we had to do manually in the sketches where the library was not used. Next, the read function retrieves the last angle set to the servo. Similarly, read microseconds returns the last pulse width that was sent. I will not use these read functions in this video, as I couldn't think of a practical use for them in a simple Arduino project. The attached function checks if the servo is currently attached to a pin and returns true or false value. Finally, we have the detach function, which disconnects the servo from its pin, stopping all control signals. Let's walk through the code examples side by side to see how they control continuous and positional servos. Starting at the top, both programs include the servo library, which allows us to use servo-specific functions. We then create a servo object. In the setup function in both codes, the servo is attached to pin 9. Since we discovered in my last video that the servo requires additional calibration, let's address it here. If you're unsure how this process works, be sure to check out the first part of this tutorial. Now let's move to the loop function, where the main differences appear. In the first example, for the continuous servo on the left, we use write microseconds function to send half a millisecond pulse, which makes the servo move forward at full speed. With delay, we keep this movement for 2 seconds. For the positional servo on the right, we use write to move the servo to the 0 degree position and hold it there for 2 seconds using delay. In the second example, in the continuous code, we send 1.5 millisecond pulse with write microseconds. This neutral pulse stops the servo movement. The delay pauses servo for 2 seconds. On the positional side, write function moves the servo to the 90 degree position, which is typically the middle point. Again, delay waits for 2 seconds. And in the third example, for the continuous servo, we send 2.5 millisecond pulse, making the servo move in reverse at full speed. The delay keeps this state for 2 seconds. On the positional side, write moves the servo to the 180 degree position and hold it there for 2 seconds using delay. So why explain these two codes side by side? Because they essentially achieve the same result. And even if you swap them around, they will work in a similar way. The main difference is that the continuous servo code uses microseconds, while the positional servo code specifies this by using angles directly. This makes coding easier and saves you hassle of extra conversions, giving you more flexibility in your projects. Let's look at the circuit I built to test both sketches. We have an Arduino Nano. This time I'm not using a power supply module. You can see the 5 volts and ground pins connected to the power rails of the breadboard. From these power rails we supply power to both the positional and continuous servos. The signal wire for both servos is connected to digital pin 9. Let's start with a sketch that implicitly provides the angle to which the servo should move. Loading, done. you can see the positional servo oscillating between three positions: 0 degrees, 90 degrees and 180 degrees, with 2-second intervals between each position. Meanwhile, the continuous servo runs at full speed in one direction, stops for 2 seconds, and then continues at full speed in the opposite direction. Now let's load the other code, which uses the write microseconds method to send pulses of 3 different lengths: half a millisecond, 1.5 milliseconds and 2.5 milliseconds. Loading. Done. You can see that both servos behave in exactly the same way. No change. Given what we have learned so far, this should not come as a surprise. Let's now try to make a servo react to the outside control information. I will use this rotary potentiometer to control the servo position. The objective here is to control positional servo using a rotary potentiometer. As previously discussed, the servo can be controlled with library methods write or write microseconds. The write method moves the servo between 0 and 180 degrees, while write microseconds operates within a pulse range of half a milliseconds to 2.5 milliseconds. The potentiometer is essentially a variable resistor that adjusts its resistance as a knob is turned, typically rotating from 0 to 270 degrees. This rotation changes the voltage at the signal pin from 0 to 5 volts. Another important range to consider is how the Arduino analog read function interprets these voltage changes. The function reads value from 0, representing 0 volts, to 1023, representing 5 volts. To control the servo using the potentiometer, you need to read the value from the potentiometer and map it to the range that corresponds to the servo's angle or pulse width. This can be done using map function, which takes 4 parameters: the minimum and maximum value of the input range and the minimum and maximum value of the output range. By converting the potentiometer reading this way, you can then send the mapped value to the servo using the write method, allowing the servo to move to the desired position. Here is the syntax of the map function. Previously I mentioned that the map function requires 4 parameters, but that was incorrect. It actually requires 5 parameters. The first parameter is the value we want to remap, followed by the source range parameters, and then the target range parameters. Now let's start writing the sketch to implement this functionality. To begin, we include the servo library, giving access to functions needed for the servo control. We create servo object. Next, we set constant pot pin for the potentiometer on analog pin A3 and constant servo pin for the servo on pin 9. Two variables, pot value and servo angle, are defined to store the potentiometer value and the mapped servo angle. In setup, we use attach method to attach the servo to pin 9. In loop, analog read function reads the potentiometer value of digital pin 9 ranging from 0 to 1023, which is then converted into an angle between 0 and 180 degrees. Then the write command sends this angle to the servo. If you want to see the values read and how they get converted in real time, you can open a serial monitor and then in the loop function add a set of print commands that will give you that information in real time. Finally, delay introduces a brief pause for smooth operation. Here is the circuit I built to test that sketch. You have the Arduino Nano at the heart of it, powered from this power supply module. You can see the ground and 5-volt pins connected to the breadboard power rails. Next, we have the rotary potentiometer. The left leg is connected to the positive side of the power supply, while the right leg is connected to the ground. The middle leg, which serves as a signal output, is connected to the Arduino's analog pin A3. Now we connect the servo to pin 9 on the Arduino. For this demonstration we are using positional servo, which can rotate within 0 to 180 degree range. The cable colors might seem confusing, especially when using DuPont jumper extension wires, so here is the visual guide to help you clarify these connections. With the servo connected, I can now power the circuit using 9-volt power supply, which the power supply module regulates down to 5 volts. Let's turn on the circuit. Initially nothing happens, which is expected as the potentiometer has not moved. However, as I start to turn the knob of the potentiometer, the servo begins to move accordingly, adjusting within 0 to 180 degree range. The servo responds smoothly and accurately to the changes in the potentiometer's position. Now let's try connecting a continuous servo to the same digital pin 9 on the Arduino. Can you guess how this servo will respond to changes from the potentiometer? Let's power up the circuit again to find out. While the positional servo shows no changes, the continuous servo rotates steadily in one direction. As I adjust the potentiometer knob, the continuous servo slows down and stops when the potentiometer reaches the midpoint. This corresponds to 1.5 millisecond signal. Turning the knob further causes the servo to accelerate in the opposite direction. Let's take a look at the serial monitor output, which shows how the potentiometer value is converted into the servo angle. Before I wrap up this video, let me show you one more project where we use external input to control the servo. This time we'll be using LM35 temperature sensor. Here's how it works. We read the temperature from the sensor, convert it into the servo angle, and create analog type temperature display with a smooth mechanical feel. I included the detailed description of this project as bonus material for channel members and on my Patreon page, so if you're interested, be sure to check it out. That's all for today. If you enjoyed this video, a like or subscription would mean a lot to me. I'll see you guys next time. Ciao.